So we are now going to put all of the pieces together. We are going to graph a function more accurately. We are going to include maxes, mins, concavity, limits, asymptotes, zeros, intercepts, everything that we know about graphing a function is going to come into play for section 4.5. So let's go over things that we should be aware of when sketching a graph. So we're going to kind of look at every piece of the process. The first thing you want to think about is what the domain is. What doesn't work? It should be the question that you ask yourself. Because if you know what does and doesn't work, you'll find any asymptotes, you'll find some of any holes of the graph, you'll find if the graph starts at one point and then continues like a square root, and things of that nature. We have to think about where it works and where it does not. Next, you want to think about any intercepts. Remember the x-intercepts. You're going to set the function equal to 0. The y-intercepts, you're going to just plug in 0. So the y-intercepts are usually easier. The x-intercepts, you might have to factor or manipulate the function to find. You can only have one y-intercept. You may have multiple x-intercepts. You may not have a y-intercept, but if you do, the most you will ever have is just one. Let's talk about symmetry. Symmetry can really help you here. Because if you know the symmetry of the function, let's say that it has y-axis symmetry. You can draw what's on one side of the y-axis accurately, and then you can just model the exact same thing on the other side. So by knowing the symmetry, we really know a lot about the function. Remember, if it's an even function, it has y-axis symmetry. And you can test that if you plug negative x in, it reverts right back to the original. If it's an odd function, when you plug in negative x, it's like you've multiplied by negative 1. Remember, that has origin symmetry. So if there's a portion of the graph in the first quadrant, there will be a portion of the graph in the third quadrant. Or opposite, if there's a portion of the graph in the second quadrant, there should be a modeled portion in the fourth quadrant. Remember, it's like a pinwheel. If I should be able to push a pin in at the origin and spin it 180 degrees, it should look like it started from the beginning. A periodic function, what that means is that every unit of p, the function repeats itself. So, that would be something like a sine or a cosine function. So we're talking waves, things that are going to repeat every so often. So sine, cosine, tangent, those are periodic functions. Let's talk about asymptotes. Now, I've gone over these asymptote rules again and again and again, but let me just quickly say that a vertical asymptote is of the form x equals a number. It is where the bottom equals 0 in a rational function or fractional function. A horizontal asymptote, we learned in pre-calculus. We also reviewed in section 4.4. And remember, that is just the end behavior, or limits to infinity. So remember, if you're dealing with fractional functions, rational functions, you're looking at that lead term on the top and the lead term on the bottom to help guide you. Increasing or decreasing. Is this function going uphill or downhill? Remember, that can be determined from our first derivative. So those critical points are going to help us. So you really want to think, what's my critical points? Where is something unique happening with our function? Next, what are the local mins and maxes? So again, that's where our first derivative changes. That might be critical points. So again, E and F are locked together. They kind of go hand in hand. You can use the second derivative test if you know first derivative equals 0. You can plug it in, but we'll talk about that more as we go through an example. You want to know the concavities and the points of inflection. So again, that would be our second derivative test. So we'll practice that. And then finally, once we have all that information, we will actually put it all together and sketch the curve. You may have to plot additional points. So in our first example, we're going to kind of go and follow the list we saw A through H on the last page, but the order in which I'll do them will be a little bit different, okay? I'm going to call step A finding the domain, but I'm also going to find intercepts at the same time, okay? So remember, this is a rational function, so you always want to set the bottom equal to 0, and you want to solve where is the bottom equal to 0. This will give us the vertical asymptotes. So those are our vertical asymptotes, but it also tells us our domain. So our domain is going to be negative infinity to negative 1, union 1 to infinity. No, I skipped a little spot. I'm sorry. Here, let me put it where
negative 1 to 1. Is that what you try to put?
Yeah. Okay. Let me move this over so we have room. So we would have that our domain goes from negative infinity to negative 1, jumps over that asymptote, goes from negative 1 to positive 1, jumps over that asymptote, and can keep going. We should have 3 sections of the graph, just like our domain has 3 sections in it. Okay. Now let's talk about any intercepts. So where does it hit the x-axis? Where does it hit the y-axis? The x-intercepts are where the function equals 0. To set a fractional function equal to 0, it is just where the top equals 0. So in this case, it would be at 0. Because 2x squared equals 0 when x is equal to 0. The y-intercept is just plugging 0 into the function. We get 0 over negative 1, which is 0. So the only place we hit the x-axis or the y-axis is at the point 0, 0. Next, does this function have symmetry? Well, the symmetry of this function, the easiest way to find it is to plug in negative x. If I plug in negative x, I get exactly what my original function is, because all of those negatives would go in a square, which would go right back to being a positive. So that tells me it is an even function with y-axis symmetry. So whatever is on one side of the y-axis is mirrored on the other side of the y-axis. So I just can use that symmetry to help me. Next, any asymptotes. You almost always do vertical asymptotes when you're doing domain. So that part's done. So now it's just a matter of horizontal asymptotes. The lead term on the top is 2x squared. The lead term on the bottom is x squared. So my horizontal asymptote is y equals 2 over 1 or 2. So that is the far end behavior is going to positive 2. Next.
We gotta go through all of these letters.
Yes. Now we're going to do increasing and decreasing. We have to find the first derivative. So the first derivative requires that we do the quotient rule. So it is the bottom times the derivative of the top.
Excuse the interruption. Well, why?
Minus the top times the derivative of the bottom, all over the bottom squared. Now let's simplify that. So there's our first derivative, negative 4x over x squared minus 1 squared. Now let's think about where we have critical points. The critical points occur where the top is equal to 0, which is at 0, and where the bottom is equal to 0, which is plus or minus 1. Now remember, there are asymptotes there. So what we have now is that if we make a plus-minus chart, we've got to put negative 1, 0, and positive 1 on that chart. I am just going to plug numbers into the entire function in one fell swoop, okay, just to save room and time and everything. So my test points are going to be negative 2, negative 1/2, positive 1/2, and positive 2. Okay. If we plug in negative 2 into the top, it's going to be a positive. Into the bottom, it's always going to be a positive. A positive divided by a positive is a positive. If we plug negative 1/2 into the top, it's going to be a positive. If we plug in negative 1/2 in the bottom, it's always going to be a positive. A positive divided by a positive is still a positive. Remember, it's undefined at negative 1. At 0, it is 0. If we plug in 1/2, we get negative over a positive, which is a negative. If we plug in 2, we get a negative over a positive, which is a negative. So what we know is that it's increasing as it approaches an asymptote. Then it is increasing again. So it's increasing from negative infinity to negative 1, and then again from negative 1 to 0. And then it is decreasing from 0 to 1, and then again after the asymptote from 1 to infinity. Now, the only point that exists as far as critical points is 0. We are increasing, then decreasing. So it is a local max when x equals 0 because it's going uphill. Hitting that point has a 0 slope of its tangent and then going downhill again.
Wait, this is high.
Okay, so we now know where it's increasing, decreasing. We have a local maximum. We know the intercepts. We know where it's hitting the x and y axis. We know symmetry. We know a lot about the graph. Now let's talk about the well, we did max and mins, so we kind of did F right here. Okay, now we're talking about G, which is the concavity and points of inflection. Okay, so we have to take the second derivative. So the second derivative is 4 times 3x squared plus 1 over x squared minus 1 cubed. Now, if you set the top equal to 0, it is never equal to 0. If you set the bottom equal to 0, we already know that. Plus or minus 1 doesn't work. So if we make our plus minus chart, the only points we have on it are plus and minus 1. I am going to plug test values into the entire function at once. My test values are going to be -2, 0, and +2. Remember, these are undefined points. If we plug -2 into the top, we get a positive. If we plug -2 into the bottom, we get a positive. A positive divided by a positive is a positive. If we plug 0 into the top, we get a positive. If we plug 0 into the bottom, we get a negative. That is a negative value. If we plug 2 into the top, we get a positive. Divided by a positive we would get in the bottom. So that's a positive value. What does that tell us? Well, there are no points of inflection. It is concave up at the ends from -infinity to -1, and then from 1 to infinity. It is concave down, like a cup that's upside down, between 0 or between -1 and +1. So we have everything you could possibly think of to graph this. So let's put on some information onto our graph. At 0, 0, we have a touchdown, so that's a point on our graph. We have I put points on the graph that I know, and I put vertical asymptotes that I know as my first two things. Now we also have end behavior horizontal asymptotes at 2. So the leftmost end and the rightmost end are heading to 2. So only at the left and right ends of my graph do I put that 2 value.